Hi everybody. In this video we will be talking about the concavity of a function's graph, and we will be exploring the relationship between the second derivative of a function and the concavity of the graph. First of all, why the concavity of a graph is important. Let's take two graphs, okay, two curves that goes from A to B, two curves where you have an increasing function. Okay, so this is an increasing function from A to B. This is also an increasing function from A to B. But the difference between these two curves is that this is increasing concave up, but this is increasing concave down. So, knowing that if a function is increasing on an interval is not enough for the graph. We also have to explore its concavity for a correct graph. Let's take a very well-known function and graph. So let us consider this function y equals x cubed. Let us graph this function. The first derivative is 3x squared, which is clearly always positive, which means we clearly have always an increasing function. If we are to graph y equals x cubed, although it's increasing always, you can see that for negative x's, it's concave down. For positive x's, it's concave up. Let's explore the tangent lines. You can see that the tangent lines for the negative x's, okay, the slopes of tangent lines are decreasing, okay? And for the positive x's, you can see that the slopes of tangent lines are increasing. So we know that the slopes of tangent lines are decreasing. We have explored what is increasing and decreasing. We know that if a function or a concept is decreasing, we know that the derivative is negative. So slopes of tangent lines derivative is negative. Here, slopes of tangent lines derivative is positive. Because it's increasing, the derivative is positive. Because it's decreasing, the derivative is positive. We know that slopes of tangent lines is in a relationship with the first derivative of a function. So we know that the derivative of the derivative is negative. Here, the derivative of the derivative is positive. So now we can move to the second derivative test for concavity. If you have a function that is twice differentiable on an interval, and the second derivative is positive on that interval, then the graph of the function over that interval is concave up. We use this notation or this form to make it shortcut. So you can see if the second derivative is positive, it's concave up. If the second derivative is negative on the interval, then the graph of the function over this interval is concave down, which is the case, okay, if the second derivative is negative, it's concave down. Let us consider these two very well-known functions in graphs. Okay, let's try to explore their concavity. The first derivative is 1 over 2x to the power minus 2 over 2, and the second derivative is minus 2 over 9x to the power minus 5 over 3. As you can see from the first derivative, this is always positive, which means the function is always an increasing function. Let's look to the concavity. Okay, you can see that if x is negative, the second derivative is going to be positive, because this is negative and this is negative, so it's going to be positive. So it's concave up. If x is positive, the second derivative is going to be negative, which is concave down. If you graph this function, this is how it looks like. So it's always increasing, but first increasing concave up, then increasing concave down. So you can see that increasing, decreasing has nothing to do with concavity. Let's take the second one. The first derivative is 2 over 2x to the power minus 1 over 3. The second derivative is minus 2 over 9x to the power minus 4 over 3. So from the first derivative, if x is negative, the first derivative is negative, so it's decreasing. If x is positive, the first derivative is positive, so it's an increasing function. But when you look to the second derivative, the sign doesn't change. It is always negative, which means it's always concave down. So although the concavity doesn't change, increasement and decreasement changes. So for the negative x's, it's concave down, decreasing. For the positive x's, it's still concave down, but now it's increasing. So from these two examples, we can see that there is no relationship between increasement and decreasement. In order to be able to graph correctly, you have to explore the concavity. A point where the graph of a function has a tangent line and where concavity changes is called a point of inflection. Okay. Has a tangent line is the key word and the key concept here that we're going to discuss in the two examples that I'm going to give in a few minutes. And we look for inflection points at points where the second derivative is 0 or the second derivative is undefined. Just be careful. It's just like we are looking for. It doesn't mean that they're going to be inflection points. Let's take these two examples. They are already known functions and known graphs for you. The first derivative is minus 1 over x squared. The second derivative is 2 over x cubed. The points where the second derivative is 0, there are none. The points where the second derivative is undefined, it's x equals 0. So if x is negative, the second derivative is going to be negative, which is going to be concave down. If x is positive, the second derivative is going to be positive, which is concave up. Let me undefined. Okay, that was a shortcut. Let me rewrite it. Okay, now let's consider the second one. The first derivative is 3x squared. The second derivative is 6x. The points where the second derivative is 0, it's x equals 0. The points where the second derivative is undefined, there are none. So we have the same candidate with these two examples, and it's the same case. If x is negative, the second derivative is negative, it's concave down. If x is positive, the second derivative is positive, it's concave up. So we have concavity changing at 0, we have concavity changing at 0. But in this case, x equals 0 is not an inflection point. X equals 0 is not an inflection point. Why is that? We return back to our key concept. A point where it has a tangent line and concavity changes is an inflection point. Here, concavity changes, all right, but the function is not defined at 0. The function doesn't have a tangent line at 0. Although the sign of the second derivative changes, it's not an inflection point. Whether in this case, if you look to the graph, x equals 0 is an inflection point. Why is that? Because the function is defined at 0, and at x equals 0, the function has a tangent line. And the concavity changes, so x equals 0 is an inflection point. Let us consider two examples, one polynomial and the other one is a rational function. To save us time, I have put down the derivatives. We're just going to discuss what is happening. Okay, so the question is, find all points of inflection, if there are any, and determine the intervals of concavity for the graph of f of x. So I wrote down the first derivative and the second derivative, and I have factorized it. So I have three factors. First of all, the first one is x squared, which is always positive. X minus 4, which is going to be 0 at 4, which is going to be negative if x is less than 4, positive if it is greater than 4. And for x plus 3, it's going to be negative if x is less than minus 3, and positive if x is greater than minus 3. So the sign of the second derivative is positive, negative, negative, and positive. Okay, now we have the points that makes the first derivative 0. We have 3 points here. The points that make the first derivative undefined, we have none. So we have 3 candidates for inflection point. Let's see which one is an inflection point, okay? Let's go back to our key concept, the point where the function has a tangent line and concavity changes, okay? So it has a tangent line everywhere because it's a polynomial, so it's defined everywhere. Let's look to the concavity. Here it's concave up, concave down, then concave up. So although we have 3 candidates for inflection, 0 is not an inflection point. Only x equals minus 3 and x equals 4 are inflection points. Let's move to this second one. I forgot to put down the derivatives, so let me put down the derivatives here. Minus x squared plus 1 over x squared minus 1 square, and the second derivative is 2x x squared plus 3 over x squared minus 1 cube. So I did these derivatives using the derivative of the quotient. I'm just putting them down to save us some time. Okay, so the points where the second derivative is 0, I have x equals 0. There are no roots from x squared plus 3 because there are no real roots. And the points where the second derivative is undefined, I have 2 candidates here. Okay, now let's look to the sign of the second derivative. Okay, so this is going to be negative if x is less than 0, positive if it is greater than 0. This is always positive, no real roots. And x squared minus 3 is going to be 0 at minus 1 and plus 1. It's going to be positive if x is less than minus 1, negative between minus 1 and 1, and it's going to be positive if it is greater than 1. So I have a negative here, I have a positive here, negative here, positive here, concave down, concave up, concave down, concave up. At first sight, it seems like we have 3 inflection points. But let's go back and look to our function and the first derivative. You can see that the function is not defined at minus 1 and 1. And it doesn't have a tangent line at minus 1 and plus 1. So although concavity changes, the only inflection point is x equals 0. After these 2 examples, I want to warn you about this implication. If the second derivative is defined at x sub 0, and x sub 0 is an inflection point of the graph of f of x, then the second derivative at x sub 0 is 0. But the converse is not always correct. That means if the second derivative is 0 at x sub 0, x sub 0 may or may not be an inflection point. Let me give you a very simple example. X to the power 4. The first derivative is 4x cubed. The second derivative is 12x squared. It's clear that the second derivative at 0 is 0, but x equals 0 is not an inflection point. Why is that? Because the second derivative is always positive. So concavity doesn't change. So not all the points that make the second derivative 0 is an inflection point. It's only a candidate for the inflection point if it changes the concavity of the graph. To sum up what we have learned in this video, let me go over the bullet points. The sign of the second derivative determines the concavity of the graph. Okay? If the second derivative is negative on an interval, it's concave down. If it is positive, it's concave up. A point x sub 0 where the graph of a function has a tangent line. Now we know that this is a very important concept. That's our key concept. And where concavity changes is an inflection point. We look for inflection points at points where the second derivative is 0 or the second derivative is undefined. But if at these points the function is defined, has a tangent line, and the sign of the second derivative changes, then these points are inflection points. In this video, I have given you an overview of concavity. I hope this video was helpful for you. The examples were simple so that you can understand the concepts. So if you want to understand this subject in depth, you have to work for more examples. Goodbye all.